Hey everybody, this is going to be the pre-lab for the limiting reactants lab. If you have a copy of this handy, you could print it or you can just have it available to read along and you can do your problems on a piece of paper. Just stay organized so that I can find it really easily when you submit it in Canvas. Okay, so this lab is going to use a setup that kind of looks like this, okay? We have a test tube and we're going to have sodium bicarbonate in there, and that is baking soda. If you didn't know that, it's baking soda. And we're going to have a syringe in the top. Now the syringe we are going to use to draw up some, stuck there. We're going to draw up about 5 milliliters of acetic acid. And then we're going to stopper this test tube. Now acetic acid is the kind of acid that you find in vinegar. So you have probably seen a vinegar and baking soda demonstration, or maybe even done one yourself. It's a pretty fizzy reaction, creates a lot of gas, okay? But acetic acid that we are using is not vinegar. It's not from a vinegar bottle. It's from something called glacial acetic acid, which is super concentrated acetic acid. And we have made several concentrations of that acetic acid. So we're going to be working with different concentrations, and we're going to learn about concentrations while we do that. So that's our setup. So let's just read through the introduction here. In this lab, you'll be reacting sodium bicarbonate with acetic acid, which if you're watching this video, you're probably going to be watching that reaction instead of actually doing it. The syringes are going to be used to capture one of the products. So yes, I've got 5 milliliters of acetic acid in here at the start of my experiment, but when I squirt that into the test tube, it's going to react with the sodium bicarbonate, the baking soda that's in the test tube. And this is going to start expanding, like this, okay? It's going to start really expanding, capturing the gas that is produced in that chemical reaction down in the bottom. Okay, so that's kind of what's happening. So the syringes will be used to capture one of the products. The amount of sodium bicarbonate used in each trial will be constant, so we're going to use the same amount of baking soda. The volume of acetic acid for each reaction will also remain constant, the volume, 5 milliliters. But the concentration of that acid will be increasing. So there will be more acid, less water within that liquid, that solution that we put in that 5 milliliters. Okay, so the total amount of acid is increasing, even though the volume is staying constant. So hopefully that makes sense. We will be observing the effects of this change on the amount of product produced. Before beginning, we must learn about how concentration of an acid is measured using a unit called molarity, which is capital M. Molarity is used to express the concentration of an aqueous solution and means moles per liter. It is the number of moles of a substance dissolved per liter of solution. So we can stop right there. If we had a whole liter of a solution and you know the molarity, then you know how many moles are in the liter. But you don't have to have a whole liter of solution. You could have 5 milliliters of a solution. And if you know its molarity, you can still figure out the number of moles, and we're going to be doing that. So if you take a look at this section just below the introduction, right above the pre-lab, we have a little factor label set up, okay? And we have X liters of HCl, and we know the molarity is Y molar, right? So molar means moles per liter, okay? So Y moles for every 1 liter, the liters cancel, and you're going to end up with just moles. And we're going to be doing that in the lab today, so I'm not going to spend too much time on the introduction part. We're going to show you that with actual numbers and the values that we're going to be using in this lab. Okay, so let me share my screen, and we're going to go through the pre-lab questions and some of the data table calculations that we need in order to be successful in this lab. So here we go. First off, the first pre-lab question says, write the balanced chemical equation for the reaction between sodium bicarbonate and acetic acid to form water, carbon dioxide, and sodium acetate. Well, sodium bicarbonate, let's just start with that. Sodium bicarbonate is baking soda, and its formula is in the materials list, but it's also maybe something that you would be able to write because sodium, we know, is Na, and it forms a +1 ion, and bicarbonate is one of our flashcards from chapter 9, which is HCO3 with a 1- charge. So a +1 and a -1 balance, and that is sodium bicarbonate. And we know that that's a solid, so we can go ahead and put a little S there. All right, acetic acid, formula for that one is also in the in the materials list. And we know that ick comes from ate. I ate something icky, right? So acetic comes from acetate. And so acetate was also one of our flashcards. It's a -1 ion, and it's the most complicated of the ions that we memorized. So HC2H3O2. Let me see if I can adjust that. Ooh. Well, I could just turn that lamp off. Hopefully that's better. Okay, HC2H3O2. And remember, our acids are going to be aqueous. They're dissolved in water. We can't really make an acid solid when it's a strong acid. Acetic acid isn't particularly strong compared to some of the others, but most of our acids, for this class, all of our acids are going to be aqueous in state. All right, react to form, and we've got the rest of our sentence here. Water, carbon dioxide, and sodium acetate. Well, we know water. Water, which is liquid. Carbon dioxide, which is a gas. And sodium acetate is NaC2H3O2. And because it has an alkali metal, we know it's going to be aqueous because there's water present in this solution. All right. So that is the equation. Now let's check for balancing. We have 1 sodium, 1 sodium. We have 1, 2, 3 carbons, or we could think of this as, well, yeah, 3 carbons, 1, 2, 3 carbons, okay? Hydrogen, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, okay? Oxygen, 3, 4, 5, 1, 2, 3, 4, 5. So it is already balanced as written, so we're lucky there. All right, number 2. Which product will we be capturing in the syringe to measure the volume produced? Well, remember when you look at your periodic table and we're looking at that molar map, we only look at volume for one type of substance, right? When we say volume at STP, we're talking about a gas. So we're trying to find the volume of a gas in this reaction. But the other clue was my setup that I showed you earlier. You're going to put a solid in here, you're going to squirt acid on it, it's going to bubble, and the syringe is going to expand as the gas that is produced fills it up, okay? So it is a gas, and there's only one product in this reaction that is a gas, and that is our carbon dioxide. So CO2 will be the product that we are measuring the volume of in this reaction. Number 3, we will be using different concentrations of acetic acid for each of the 3 reactions. Why is it important that we use the same volume of acetic acid in each reaction? Remember, I'm going to start off with 5 milliliters of the acid, and it might be more concentrated, so there's more moles there, but it's important that we start with just 5 milliliters each time. And part of that is when I push that into the test tube, even if there was no chemical reaction, 5 milliliters of gas would be displaced in the test tube. And if you look, it's coming back up to 5 milliliters without me even touching it, okay? So we want to make sure that we use a constant volume so we can subtract that constant volume each time and end up with accurate results, okay? So what are we going to write here? We need a consistent starting volume. We need a consistent starting volume. When you squirt that 5 milliliters of acetic acid in there, 5 milliliters of gas is going to automatically displace that acetic acid, right? So that's our starting volume, 5 mils. Then we're going to be measuring the CO2 produced by how far the plunger is pushed beyond that 5 milliliter mark, okay? So we need a consistent starting volume is how I would word that. Okay, number 4, we will be using 5 milliliters of acetic acid in each reaction. How many liters is this? Reaching all the way back to our chapter 3, maybe, when we were doing metric conversions, okay? Now I read that as 5 milliliters. It's 5.0 milliliters, sig figs, okay? Milli is the little m on our line. Liters is in the standard, which is our S. The liters are bigger, so 1 liter. If you count your spaces, you get 3 zeros, 1,000 milliliters in a liter, and that's it. So 5 divided by 1,000. Now, if you do that in the calculator, you're going to end up with 0.005. Makes sense? Move this over 3 times, right? Sig figs, though, pay attention. That is only 1 sig fig because lefties don't count, okay? We need it to have 2 sig figs because of this righty over here. So we need to add a 0 at the end to show that we still have 2 sig figs in our answer, okay? All right. Calculate the volume of carbon dioxide that will be produced if 0.15 grams of NaHCO3 react completely with the acetic acid. I'm going to squeeze it in here. And then we're going to convert it to liters as well. So we'll see if I have space for that. But our starting point is 0.15 grams NaHCO3. Whenever you're starting in grams, your first step is automatically molar mass. 1 mole of NaHCO3. I need to figure that out real quick. So my oxygens, 3 times 16, plus my carbon is 12, plus my hydrogen is 1, plus my sodium, which I believe is 23. Yep. We get 84.0 grams of NaHCO3. All right. We are trying to find the volume of carbon dioxide, volume, okay? First, we need our mole ratio, though, which everything is 1 to 1, but 1 mole of baking soda for every 1 mole of carbon dioxide. And again, we're sticking to STP conditions for our calculations. 1 mole of CO2 is 22.4 liters of CO2. I think earlier I said we're going to convert this to liters. We're actually going to convert it to milliliters, but here we go. Okay. We'll just scoot that up right there. So when we punch this one in, 0.15 divided by 84 times 22.4, we're going to end up with 0.04. And again, 2 sig figs right there, 2 sig figs. So I need to add a 0 here to make it the right number of sig figs, liters of CO2. Okay, 0.040 liters of CO2. You're going to have to write that down, box it. Then we're going to use that to convert to milliliters, which is the opposite of this conversion right here. 1 liter is the same as 1,000 milliliters. Excuse me. And we're going to end up with 40 milliliters CO2. Okay. So in our reactions in this lab, if all of this reacts, all of our baking soda reacts, we're going to end up with 40 milliliters of CO2 in this syringe. All right, that's the pre-lab, but we're not done yet. Don't stop this video. We need to get to our data table. This is what your data table looks like. If you haven't printed this, copying it, if you can try to copy it, you're going to need workspace inside this data table so that you can show your work. If you don't show your work in your data table, you definitely need to make it obvious where that work is so you can get full credit. But get to that page. Remember this 40 milliliters value because we are going to put it at the top of that page. So in this line where it says, if all of the NaHCO3 reacts, how many milliliters of CO2 are produced, right? This is from question 5 on the previous page. 40 milliliters if all of the baking soda reacts. If all of the baking soda reacts, we're going to get 40 milliliters of CO2. Now notice I put that point. I probably should have done that on the other page. I forgot. To get this 0 to count, remember, righties only count if the decimal point is written. So this is 40 with a decimal point to get that 0 to count. Okay, so that's 40 milliliters. Okay, now we're going to go through this table and we're going to fill in several things. So first of all, if we look at this section, let me see if I can zoom this in here. Ooh, okay. If you look at this, our first acetic acid, let me see if I can just write on this, okay, is 0.20 molar, 0.20 molar. Our second one is 0.40 molar. And our third one is 0.60 molar. Okay, I keep saying that molar, molar, molar. Remember, this is a new term for us. That capital M means moles per liter, moles per liter, moles per liter, moles per liter. So our first reaction, the acetic acid only has 0.2 moles for every liter, but we're not using a liter. We're only using 0.0050 liters, right? This is the result of question number 4 on our pre-lab, okay? We're using 5 milliliters, which is 0.0050 liters. Well, when we multiply that times 0.2, my liters cancel out. So 0.0050 times 0.2, and we end up with 0.0010 moles of acetic acid because the liters cancel out. Again, we're keeping that 0 in order to have 2 sig figs. These lefties don't count as sig figs. They're just placeholders. So same here. If I have 0.4 molar, that's 0.4 moles per liter, but I'm only using 0.0050 liters. The liters cancel out when I multiply these two together, and I'm going to end up with 0.0020 moles of acetic acid, 0.0020. Okay, and then down here, 0.0030 moles of acetic acid. Okay, now, volume of CO2 that should be produced if all of the acid reacts. Well, we need to start with the moles of acid. I'm going to do A over here. All right, let me zoom back out here. See if we can get that clear. Okay, so for part A, reaction A, okay, volume of CO2 if all acid reacts, but I'm going to put liters, okay? All right, if all the acid reacts, volume of CO2 in liters. Okay, so we're going to start with moles of acid. We just calculate the moles of the acid, or it's given to you there, so 0.0010 moles of the acid. Okay, I'm going to just put, well, I'll put the formula for the acid, HC2H3O2. Whoa, that's not a 2. Okay, I want to get from moles to volume of CO2. So I'm going from moles of A to volume of B. So my mole ratios, remember in that equation, all of the mole ratios are 1 to 1 to 1, okay? So, excuse me, 1 mole HC2H3O2 for every 1 mole of CO2. And then 1 mole of CO2 is 22.4 liters. Molar volume. Okay? So 0.0010 times 22.4, and we get 0.0224 liters, which really sig fig wise should just be 0.022 liters of CO2. 0.0022 liters of CO2. Okay. Our next section of the data table is asking for that same volume in milliliters. So a little less work here, 0.022 liters. 1 liter is 1,000 milliliters. And that's it. Multiply this by 1,000, we get 22 milliliters of CO2. Okay, our next column is asking for the limiting reactant, okay? So I'm sorry that I'm not doing this in columns, but all of this is for reaction A, okay? I'm doing it in rows, you've got it in columns, but you can follow along, I'm sure. Limiting reactant, remember, I'm gonna write NaHCO3 up here. If all of the baking soda reacts, we're gonna get 40 milliliters of CO2. If all of the acid reacts in reaction A, we're going to get 22 milliliters of CO2. 40 milliliters versus 22 milliliters. Which one is limiting, the baking soda or the acid? Remember, the smaller answer tells you which one is your limiting reactant. So for reaction A, HC2H3O2 is the limiting reactant. So you can put that in our third column that we need to fill in here because it gives less CO2, okay? Or you could write something like 22 milliliters is less than 40 milliliters, right? So it gives less CO2. That's your limiting reactant. So the next column says, what is your theoretical yield? Okay, remember, our theoretical yield is what we should be able to make. Well, at 22 milliliters, the reaction is stopping. We can't make any more than that. But again, that 22 milliliters is perfect. If we're in a perfect world at STP, that's how much we should get, right? So our theoretical yield for reaction A, I'm going to write TY for theoretical yield, is 22 milliliters. Then the reaction stops. We can never get to 40 because the reaction is going to run out of acid. Okay? All right. I want you to go through these calculations and this analysis for reaction B and reaction C. Pause the video, show your work, get all the answers, and then press play on the video, and I will tell you what your theoretical yields are. And if they don't match on your worksheet, then you're going to need to reach out to me before you do your lab. Otherwise, all your post-lab questions are going to be wrong as well. So pause the video, come back, I'll tell you the answers. You can check. If you don't show work on this, you're losing major points, and labs are worth a lot. So don't try and cheat, okay? Pause it, try it. Contact me if you're not getting the right answers after you start the video again. Okay, after having done reaction A together, now you've done B and C. Hopefully you've tried them and hopefully you've succeeded. So here's what we would get. Reaction B should, your volume of CO2 in milliliters should be 45, which makes your baking soda limiting because it can only make 40 and you run out of baking soda. And that makes your theoretical yield 40 because after that, the baking soda is gone, you cannot make any more. For reaction C, the volume of CO2 in milliliters should be 67. Your limiting reactant is baking soda, NaHCO3, sodium bicarbonate, because it only makes 40. 40 is way less than 67. Baking soda runs out, reaction stops. So your theoretical yield is 40, not 67, 40. The lower number is your theoretical yield. The actual yields are going to come from the lab video that shows you these chemical reactions. So don't fill anything else out. You're going to need to submit pictures of the pre-lab and of your data table with all your calculations and your theoretical yields complete. And that will give you your pre-lab credit. And then you can move on to the actual lab when it unlocks in the module. Thank you for watching. And again, please reach out if you need any help. We'll see you later.